I'm Antonio Sala, and in this video we are going to model a carousel, its dynamics, accelerations, whatever. Our final goal will be, let's say, understanding how to carry out simulation and animation of the one passenger merry-go-round dynamics to see how this oscillates depending on the speed of the rotating platform, etc. But of course, in order to do that, we need to obtain the equations of motion. So that would be the objective of this first video. Well, in fact, we will make a lot of simplifying assumptions, of course. In particular, we will consider something just like this. We will have a central rotation axis. We will have a platform, not necessarily in the form of a bar, of course, it can be a circle of whatever shape. The only important thing in the equations will be its rotational moment of inertia, I0. And then at a distance r0 from this central axis of rotation, we will suspend a mass with a rope or a chain or whatever of length L. The mass will be capital M, and then that mass may have an extra angular motion theta. This joint will not be a spherical one, so we will assume it can only move in one degree of freedom here, so it can just turn in the plane formed by the z-axis and the real or imaginary line joining the center of rotation of the platform and the hinge to suspend this mass. So, in summary, my movement will have two mechanical degrees of freedom, this angle phi and this angle theta. So we will define them as symbolic variables in this line, and in this line we will define also symbols for the constant parameters of my model, moments of inertia, masses, a couple of lengths, and the gravitational constant. In order to help MATLAB with the simplifications to put things in pretty form, I will tell MATLAB that all this stuff is going to be positive, just in case it helps. So, once we stated our problem, determining the equations of motion of this simplified carousel model, we'll discuss the kinematics. What is kinematics? Well, expressing the position of this mass, which I will shorthand as lowercase r, and its velocity and its acceleration as a function of these angular degrees of freedom, angular coordinates, and their velocities and accelerations, angular velocities and angular accelerations. Writing that thing is called kinematics. And basically it will amount to apply chain rule because, well, if I define the coordinate vector q with the angles phi and theta, then r is a function of q, and of course, as q is a function of time, this angle changes with time, then we'll need to apply chain rule to obtain time derivatives of this suspended mass position. So let's delve into the details. The first thing to address will be, well, just position kinematics. I mean, which is this expression of the position of the end mass? So we'll need to carry out a bit of trigonometry. Basically, in my code, I will denote this distance from the center to the projection onto the xy plane of the mass position. I will denote that as capital R, and of course it will be R0 plus L times the sine of theta. So x will be this capital R times cosine of phi, and y will be r times the sine, and well, the z coordinate will be, well, down from this level minus L times cosine of theta. But, well, in my code, I changed the origin of my vertical reference system so that, arbitrarily, of course, I called theta equals 0 the downward equilibrium position when everything is stopped. In that way, zeta will be always positive in my equations, and in order to say that, well, we need just to add L to my previous expression. So this is what I wrote here in MATLAB Symbolic toolbox code. So this is R of Q position to position transformation, being Q the vector of the two angles, and then now in order to progress further with velocities and acceleration, I will need to define angular velocities and angular accelerations. So I do that in these two lines of MATLAB, and in the same way as I arranged the positions in a vector Q, then I will have a vector of velocities VQ and a vector of accelerations AQ. Of course, you can name it as you wish, but in fact, in physics books, usually the vector of angular speeds will be denoted as .q, defined with these omegas in my particular notation choice, and the vector of angular accelerations will be denoted by a double dot notation, but I denote alpha 0 and alpha 1, these two angular accelerations, so well, you need to understand the dot notation or whatever, but it's just a cosmetic issue. So once we have defined the position, velocities and acceleration vectors of my angular coordinates defining the movement of this carousel, then we can apply chain rule to obtain the time derivatives of the position of the suspended mass. So let's go with the speed of the suspended mass, of course in 3D space because it has x, y, z changing with time. Then, as angles are themselves functions of time, in order to obtain, let's say, the speed in the x direction, I will need to take partial derivatives of this and then multiply by the time derivative of the angle, and do this thing 3 times. But, well, in the theory books, these kind of manipulations are represented in the abstract notation, saying that if I take partial derivatives with respect to the angles and multiply by the angular speeds, then I get an expression which is the velocity of the suspended mass that depends on the angles and their speeds. This is in abstract physics book notation. In MATLAB, well, taking a lot of partial derivatives is carried out with the Jacobian command. So this takes the partial derivatives of the 3 position with respect to the 2 angles, so this is a 3 times 2 matrix, and then if I multiply by the angular speeds, which is a 2 times 1 vector, then I get a velocity vector, which is of course of dimensions 3 times 1, everything agrees with what we expect. And then we have an expression in which of course angular positions and angular speeds of my coordinates defining motion do appear. If we wish to compute accelerations, then again, as phi is a function of time, omega 0 is a function of time, theta is a function of time, and omega 1 is a function of time, then I will need to carry out 4 partial derivatives times some time derivatives of these letters. So in abstract form is this thing, partial derivatives with the letters representing angular positions will need to be multiplied by angular speeds, the time derivatives of the positions, and the partial derivatives with respect to letters representing speeds will need to be multiplied by the time derivatives of the speeds, which is the angular accelerations. So this thing here in abstract notation ends up being this highlighted segment of MATLAB code, apart from the simplified stuff to try to write things in pretty form. So I take the partial derivatives of the velocity with respect to positions and multiply by velocities, and the partial derivatives of the velocity with respect to angular velocities, and I multiply them by accelerations, so we end with this horrible stuff that defines the acceleration of the suspended mass as a function of the position, velocities, and acceleration of the angular coordinates I'm using to describe my motion. So this is the kinematics, but acceleration is not needed in Euler Lagrange methodology we are going to follow. If we were doing force and torque balances, then we would say that mass or moment of inertia times acceleration is equal to some force balance. So we will explicitly need this acceleration formula, but in the Euler Lagrange, accelerations will appear in a slightly different way. Let's delve into the details. The basic idea of the Euler Lagrange equations of motion is that they are based in energy balances, sort of. So we need kinetic energy, capital T, and potential energy, capital V. How do we define kinetic energy? Well, this thing is the kinetic energy of the suspended mass, 1/2 mass times velocity squared, and of course, as velocity is a vector, we need to put the modulus of the velocity vector squared, which is vector transposed times itself. And this is the kinetic energy due to the rotation of the top platform from which things hang, which is 1/2 moment of inertia times angular speed squared. So adding these two components, we have the overall kinetic energy of our system, and then potential energy is just mass times gravity constant times height, and then with that kinetic and potential energies, we define the so-called Lagrangian as the difference between those energies. So good, once we have the Lagrangian, the equations of motion need defining this intermediate variable that is called generalized momentum, which is the partial derivatives of the Lagrangian with respect to angular speeds. So I get this thing as the first component and this thing as the second component. I get it in row form, I mean no problem, but I will put some transposes later on to have my equations in column form, but it's just cosmetic. So well, this is the generalized momentum, and the Euler Lagrange equations of motion tell me that for each of the two components of this momentum vector, I need to write this, and this is the equation of motion. Its time derivative is equal to the torque applied at each angular joint. I will here have some torque, tau, in theory tau, let's say 0 or whatever, tau applied there. And in here, if I had a fully actuated mechanism, I might place there another motor, but in here I will assume that there is no motor there, no torque. So this is a hinge moving freely, let's say, no actuation there, no power. So I will have external torque only in the first equation of motion. And then, well, let's do that with MATLAB. Of course, as this P is something in which I get angular positions, look at this theta here, and angular speeds, look at this omega 1 and omega 0, then I need to carry out chain rule as I did with the acceleration. That's why I explained it, even if we were not explicitly using it. We were doing the same chain rule stuff that we are now doing here. I will need to take derivatives with respect to positions and multiply by speeds, and derivatives with respect to speeds and multiply by accelerations. So this is the PDT, a horrible thing I don't wish to look at, because, well, I will just write this equation of motion in MATLAB's symbolic toolbox as this thing. First joint I will assume actuated by torque tau, and second joint I will assume it not actuated, so no torque in this joint here, and this is this, this is this, and well, I have some kind of transposed thing here because, well, I arranged things so that the equations of motion are a column of equations instead of a row, but it's nothing important. So at the end, MATLAB obtains this thing here as the equations of motion that, okay, they are correct, we can work with them, but in most books in mechanics or robotics, these equations of motions are equivalently rewritten by just letting accelerations at the left-hand side and things that do not involve accelerations at the right-hand side. So this is the usual way you will find the equations of motion in robotics books, for instance. What multiplies accelerations is called mass matrix. In the first equation, this is what multiplies acceleration, and in the second equation, it is this thing. So we have a diagonal mass matrix in this case, but of course, as these accelerations are angular accelerations, in fact, the dimensions or the meaning of the thing that multiplies accelerations is, of course, a moment of inertia, say equivalent inertia or something like that. Well, the thing is that we have a mass times acceleration or inertia times angular acceleration actually equal to some balance of torques, forces, whatever. In this way, we have the external torques. Then we have some Coriolis or centrifugal force or things like that, usually depending on the squares of speeds. This coupling term depending on this product of angular speeds affecting the platform. And we have this second coupling term in the equations of the suspended mass, introducing, let's say, a centrifugal force depending on the square of the platform's rotation speed. And then we have this gravity-related term depending on angular positions. So the combination of all these are the equations of motion, but of course this is just a usual way of writing them so that we can interpret them as, equivalent inertia or whatever, but Euler Lagrange say that independently of how you later rearrange this, the kinetic and potential energies define the equations of movement if you write this, i.e. this. So we end with this. In this video, we made an abstraction of this carousel, transforming it to this problem, and we obtained the equations of motion via the Euler Lagrange equation with a lot of help from MATLAB's symbolic toolbox. In particular, we used a lot of times the Jacobian command. So we end here. Thanks for watching.